Imagine something so large that if you replaced our sun with it, its edge wouldn't stop at Mercury, or Mars, or Jupiter, or Pluto. It would keep going, past the edge of our entire solar system, and still not be done. That thing exists. Probably. And that probably is the problem. Let's start with what we know for certain. In 2010, a telescope at the South Pole, not searching for black holes, not even searching for galaxies, but hunting for faint bruises in the oldest light in the universe, found something strange in the constellation Phoenix. A cluster of roughly 1,000 galaxies, all bound together by gravity, radiating X-rays so intensely it stood out from everything else in the survey like a bonfire in a dark field. It was called the Phoenix Cluster. 2 years later, MIT astronomer Michael McDonald pointed NASA's Chandra X-ray Observatory at it. What he saw shouldn't have existed. Every galaxy cluster ever studied up to that point followed the same rule. The central galaxy is dead, quiet, starless. The supermassive black hole at its core heats surrounding gas, blasts it outward, and the result is a kind of cosmic deep freeze. Star formation stops, the galaxy goes silent. The Phoenix Cluster's central galaxy was producing stars at 740 per year. Our entire Milky Way manages one. McDonald described what he was seeing as a cooling flow, gas that had finally, impossibly, started shedding its heat instead of being blasted away. Like a cup of coffee that was supposed to stay hot forever, except it was actually going cold. A 10 million degree cup of coffee, he said, but still, eventually, physics wins. And at the center of all of this, at the heart of this impossible star factory, sat the black hole astronomers would come to call Phoenix A. Now, here's where the story gets complicated and contested. In 2016, a theoretical paper tried to estimate the mass of Phoenix A. The method used was a well-established one. Look at the size and velocity of the galaxy hosting the black hole. Bigger galaxy, bigger black hole. It's a correlation that holds across thousands of observations. The number that came out was 100 billion solar masses. That figure spread across the internet like wildfire. 100 billion suns collapsed into a single point, an event horizon, the boundary of no return, stretching 2,000 astronomical units across. To put that in perspective, if you placed Phoenix A where our sun is, its event horizon alone would swallow the inner edge of the Oort cloud. Our entire solar system would vanish inside it without touching the sides. It would be bigger than TON 618, the previous record holder at somewhere between 40 and 66 billion solar masses, by more than double. It would be, as far as humanity could detect, the largest single object in the observable universe. But in 2019, Michael McDonald, the man who found the Phoenix Cluster in the first place, went back to the data. This time, with more of it. Direct X-ray measurements from Chandra, infrared from Hubble, radio observations from the Very Large Array. His published figure? 5.8 billion solar masses. Not 100 billion, not even close. A number that would place Phoenix A firmly in the category of large but not extraordinary, well behind TON 618. So which is it? 5.8 billion or 100 billion? The honest answer is, we don't know. And that uncertainty isn't a failure of science. It's a window into something genuinely hard. To measure a black hole properly, you need to watch things orbit it. Actual stars, tracing paths through space over years. That's how we confirmed Sagittarius A star, the black hole at our galaxy's center, at 4 million solar masses. Decades of watching stars whip around an invisible point with the precision of a clockmaker. Phoenix A is 5.8 billion light-years away. We cannot resolve individual stars anywhere near it. We are working from shadows. McDonald's lower estimate is based on the temperature and density of the X-ray gas around the black hole, a legitimate technique, but one that measures the environment, not the object. The higher estimate is based on a galaxy scaling relation, equally legitimate, but an indirect correlation built from observations of different objects entirely. Both methods have systematic uncertainties that can shift the answer by factors of 10 or more. The two numbers aren't equally likely to be right, but neither can be ruled out. Here is why the 100 billion number matters beyond bragging rights. In 2016, Yale astrophysicist Priyamvada Natarajan calculated what she believed was the universe's self-imposed maximum, the point at which a black hole's own energy, the furious radiation pouring from its accretion disk, overwhelms the inflow of gas feeding it. The black hole essentially suffocates itself. Her limit was approximately 50 billion solar masses for a non-spinning black hole, climbing toward 100 billion if the black hole spins rapidly in the same direction as its host galaxy. Beyond that, physics, as we understand it, says growth stops. If Phoenix A is truly sitting at 100 billion solar masses, it is at the edge of the universe's construction limit, the largest thing the laws of physics will ever permit to exist. But a group of researchers pushing the boundaries of theory even further have proposed that this ceiling may not be absolute. In 2020, they coined a name for what might lie beyond it: stupendously large black holes, SLABs, objects exceeding 100 billion solar masses. Their proposed formation pathway isn't through normal galaxy evolution, but through a primordial route: black holes seeded in the first moments after the Big Bang, before the first stars ever formed, growing quietly in the dark for billions of years. No SLAB has ever been confirmed. Phoenix A, depending on which measurement you trust, might be approaching the threshold, or might already be past it. And Phoenix A is still growing. In February 2025, a team led by MIT researcher Michael Reif published results in Nature from an unprecedented 12-hour observation of the Phoenix cluster using the James Webb Space Telescope. They mapped a previously invisible layer of gas, warm gas around 300,000 degrees Kelvin, hotter than the cold molecular gas that forms stars, but far cooler than the million-degree intracluster medium above it, flowing steadily inward toward the central galaxy, toward Phoenix A. They found clumps and filaments of this cooling gas threaded through the core of the cluster. Gas at every temperature, in every phase of the transition from hot to cold, falling together in the same direction. It was the first time scientists had directly imaged a complete cooling flow, something theorized for decades, but never before seen in full. The mass falling inward and cooling every year, somewhere between 5,000 and 23,000 times the mass of the Sun, every year. Some of that becomes stars. Some of it may become Phoenix A. The Phoenix cluster, McDonald has said, remains the only object of its kind ever discovered. Not approximately unique, categorically unique. 13 years of searching have not produced a second one. It is a laboratory for physics that should not exist. A galaxy cluster where the ordinary rules broke down, where a cooling flow survived and flourished, where a starburst raged at a rate 700 times our galaxy's output, and where a black hole of uncertain, but almost certainly extraordinary mass sits at the center of it all, still feeding. The deepest question here isn't actually about size, it's about limits. The universe appears to set rules. Black holes grow until their own energy stops them. Star formation is eventually strangled. Cooling flows are eventually shut off. The Phoenix cluster seems to have violated at least one of those rules. Its black hole may be violating another. And if Phoenix A is truly as massive as the highest estimates suggest, if it really sits at the theoretical ceiling of what the universe permits, then what we're watching is the closing act of something that took billions of years to build. A black hole at the absolute edge of what physics allows, eating its final meals, growing imperceptibly toward a size the universe itself may not be able to sustain. We found it just in time to watch it finish.